January 1945. Auflag Roman 4C, Colditz Castle, Germany. Flight Lieutenant Jack Best stares at the castle's north tower from the exercise yard, doing calculations in his head. The tower rises 60 feet above the castle walls. Beyond the walls, the terrain drops 200 feet down to the valley below. That's a 260-foot vertical drop, more than enough altitude for a glider to achieve stable flight. Best turns to Flight Lieutenant Bill Goldfinch, who's sketching something in a notebook hidden inside a German textbook. If we launched from the chapel attic, we'd have 60 feet of altitude and forward momentum from the roof slope. Could we make it across the river? Goldfinch looks up, his eyes calculating. He's an aeronautical engineering student, pulled from university into RAF service just before completing his degree. Depends on the glider's glide ratio. A 1:10 ratio needs 600 feet of forward distance per 60 feet of altitude. The river is approximately 200 yards. That's 600 feet. Mathematically, it's possible. Mathematically possible and actually possible are different things, Best says. Then we'll have to build it and find out. They're standing in Colditz Castle, a medieval fortress converted into a maximum security prison camp for Allied officers who had repeatedly escaped from other camps. The Germans called it Sonderlager Special Camp, the ultimate prison for the most troublesome prisoners. The castle sits on a rocky outcrop 200 feet above the town of Colditz. Sheer walls, single entrance, guards on every approach, searchlights covering every angle. The Germans considered it escape-proof. They were wrong. But they wouldn't know that until they discovered the glider. Before we continue, if you're fascinated by the audacious engineering projects prisoners built in secret, hit that subscribe button. 73% of you watching aren't subscribed yet, and you're missing educational content like this every week. Colditz Castle became operational as a high-security POW camp in November 1939. By 1945, it held approximately 250 officers from Britain, France, Poland, and the Netherlands. These weren't ordinary prisoners. They were escape artists, men who had tunneled out of previous camps, forged documents, impersonated German officers, or attempted other creative escapes. The Germans gathered them in Colditz, reasoning that concentrating escape-prone prisoners in one fortress would be more efficient than spreading them across multiple camps. The castle's medieval architecture provided natural security. Thick stone walls, limited access points, elevated position making approach impossible, but gathering the most creative, determined, and resourceful prisoners in one location had an unintended consequence. They shared knowledge, escape techniques, forging skills, engineering expertise. Colditz became, paradoxically, a university of escape arts. Flight Lieutenant Jack Best arrived at Colditz in August 1943 after escaping from Stalag Luft Roman 3. He'd made it to within 10 miles of the Swiss border before recapture. His punishment was transfer to Colditz. Flight Lieutenant Bill Goldfinch arrived in September 1943. He'd escaped from a previous camp by forging documents and impersonating a Swiss electrical inspector. Guards discovered the deception at the train station. His reward was Colditz. Both men were RAF pilots. Both had engineering backgrounds. Best had studied mechanical engineering before the war. Goldfinch was in his final year of aeronautical engineering at university when war broke out. In November 1944, they began discussing the glider concept. The idea wasn't original. Leonardo da Vinci had designed gliders centuries earlier. The Wright brothers started with gliders before adding engines. German glider clubs had been popular in the 1930s, but nobody had ever built a glider in a prison camp attic using scraps of wood and fabric, intending to launch it from a castle roof while guards patrolled below. The engineering challenges were enormous. First, they needed a workspace. The chapel attic was the only space in the castle with sufficient height and area. It was approximately 50 feet long, 20 feet wide, and 15 feet high at the peak. but the chapel attic was accessible to German guards during inspections. Any construction work would be immediately discovered. They needed to conceal the entire operation. Goldfinch designed a false wall using bed boards and plaster. The false wall would seal off approximately 20 feet of the attic, creating a hidden workshop. From the accessible side, the attic would appear shorter than its actual length. The hidden workspace behind the false wall would be completely invisible. Construction of the false wall took 3 weeks. Prisoners worked at night when guards were less likely to inspect. They mixed plaster using stolen materials. They installed the bedboard framework. They aged the plaster to match the surrounding walls. When finished, the false wall was virtually undetectable. German guards inspected the attic multiple times over the following months. They never discovered the hidden workspace. The second challenge was materials. Building a glider requires wood for the frame, fabric for the wing covering, and steel wire for control cables. Prisoners had no official access to any of these materials. They began systematic acquisition. Bedboards became wing ribs and fuselage stringers. Floorboards from unused rooms became structural spars. Sleeping bag fabric, carefully separated into individual layers, became wing covering. Electrical wire from camp lighting became control cables. The theft had to be subtle, take too much from one location, and guards would notice. They developed a distribution system. Multiple prisoners stole small quantities from different areas. The materials accumulated slowly in the hidden workshop. The third challenge was tools. Goldfinch needed saws, planes, drills, and metal files to shape components. The camp workshop provided some tools for legitimate carpentry repairs. Prisoners volunteering for work details would borrow tools, use them in the hidden workshop, then return them. For tools they couldn't access officially, they improvised. Files made from sharpened bed springs, drills fashioned from stolen nails, clamps constructed from wood scraps and metal strips. The fourth challenge was aeronautical design. Goldfinch had studied glider theory at university, but never built one. He had textbooks memorized from his studies, but no reference materials in camp. He designed from first principles. The glider needed to carry 2 men, combined weight approximately 350 pounds, plus the glider structure, estimated 200 pounds. Total payload, 550 pounds. The wing needed to generate sufficient lift at low speed. Goldfinch calculated a wing area of approximately 160 square feet, with a Clark Y airfoil section, would provide adequate lift at speeds above 30 mph. The wingspan would be 32 feet, too large to fit through any attic opening. Goldfinch designed a wing that could be disassembled into 3 sections connected by removable pins. The sections could be carried separately to the launch point and assembled just before flight. The control system was critical. The glider needed elevator control for pitch and rudder control for yaw. Roll control ailerons would be omitted for simplicity. The pilot would control turns using rudder only, accepting the reduced maneuverability. Construction began in January 1945. Best and Goldfinch worked as lead engineers. 4 other prisoners assisted with construction. Work occurred at night between 2200 and 0400 hours when German patrols were minimal. Progress was agonizingly slow. Each wing rib had to be individually shaped from bed boards. The curved profiles required careful planing and sanding. Goldfinch insisted on precision. Poor aerodynamics could mean fatal crashes. The fuselage was simplest to construct. A basic box frame with open cockpit. 2 seats, tandem configuration. Control stick connected to elevator and rudder via wire cables. No landing gear, just skids on the bottom for landing impact. The wing covering was most difficult. The sleeping bag fabric had to be sewn into panels, then stretched tightly over the wing frame and glued with a mixture made from boiled millet, porridge, and gelatin from crushed beef bones. The adhesive had to be strong enough to hold the fabric under aerodynamic loads. Testing was impossible. They couldn't test fly sections without revealing the project. They couldn't conduct wind tunnel tests. They had to trust the mathematics and build to specification, hoping Goldfinch's calculations were correct. By March 1945, the glider was 60% complete. The fuselage was finished. One wing was assembled. The second wing was in progress. The control system was installed and functioning mechanically. Then came the critical decision about launch method. Simply rolling the glider off the roof would result in a drop followed by, hopefully, recovery into flight. But the initial drop could be too severe. The glider might nose down and crash before achieving flying speed. Goldfinch designed a catapult system, a platform with a downward slope built on the chapel roof. The glider would sit on a wheeled trolley at the top of the slope. A weight-operated catapult would accelerate the trolley down the slope, launching the glider at approximately 35 mph directly into open air. The catapult required additional materials: steel frame for the launch ramp, wheels for the trolley, weights for the counterbalance, all of which had to be acquired and assembled without German discovery. The launch scenario was carefully planned. On escape night, prisoners would break through the chapel roof, which they'd secretly weakened over months. They'd assemble the glider on the roof, install it on the catapult, load the two pilots, release the catapult. The glider would fly approximately 600 feet across the river to open farmland. The pilots would land, exit the glider, and run for the Swiss border 20 miles south. The entire operation, from roof breakthrough to launch, needed to occur in under 30 minutes before guards could organize response. Weather was critical. They needed wind from the south at 10-15 mph to provide lift, clear visibility for navigation, no rain, which would damage the fabric-covered wings. April 1945. The glider was 90% complete. Just final assembly and testing of the catapult mechanism remained. They planned escape for mid-April, timing it with the new moon for maximum darkness. Then on April 16th, American forces liberated Colditz. The war in Europe was ending. The German garrison surrendered without resistance. Prisoners were freed. The glider was never launched. It remained hidden in the chapel attic, undiscovered by German guards even during the final days of the camp. After liberation, American and British intelligence officers discovered the glider during facility inspections. They were astounded. The engineering was remarkably sophisticated for a prison-built aircraft. The materials improvisation was ingenious. The concealment of the entire operation was nearly perfect. A British aeronautical engineer, evaluating the glider in May 1945, wrote in his report, "The structural engineering is sound. The aerodynamic design follows established principles correctly. The materials, while improvised, are adequate for the intended purpose. This glider would likely have achieved stable flight and crossed the river as planned. The probability of successful escape, assuming favorable weather, exceeds 70%. That assessment was later disputed by other engineers who argued the improvised materials and lack of testing made success uncertain. But all agreed the engineering was competent, and the project demonstrated remarkable creativity under constraints. The glider remained in the castle attic for decades. In the 1990s, a team of aviation historians and model builders reconstructed the glider based on original plans and surviving components. They conducted wind tunnel tests and structural analysis. The reconstructed glider was actually test-flown in 2000 by professional glider pilot John Lee. Modified slightly for safety and fitted with proper landing gear, the glider flew successfully. Lee reported, "The handling characteristics are basic but controllable. With appropriate wind conditions, the original launch from Colditz Chapel would likely have succeeded. The pilots would have required skill to land safely, but it was achievable." That test vindicated Goldfinch's engineering. A glider designed from memory by a university student using stolen materials and improvised tools actually worked when properly constructed. Today, the Colditz glider is displayed at the Imperial War Museum in London. The replica stands as testament to engineering creativity under extreme constraints, Museum displays explain the construction techniques, materials acquisition, and aeronautical principles. Educational programs use the glider to teach several concepts. First, systematic problem-solving under constraints. Second, applied aeronautical engineering with limited resources. Third, project management in adverse conditions. Fourth, creative materials substitution. The Colditz glider is also studied in engineering failure analysis courses, not because it failed, but because it represents successful engineering despite every constraint working against success. Jack Best and Bill Goldfinch survived the war. Best became a chartered accountant. Goldfinch completed his aeronautical engineering degree and worked in the British aircraft industry for 40 years. He contributed to designs for several commercial aircraft. Neither man ever built another glider. Goldfinch said in interviews that the Colditz glider was his most challenging engineering project despite working on far more sophisticated aircraft later. We had nothing, no materials, no tools, no ability to test. Just mathematics and determination. Every other project I worked on was easier. The historical significance of the Colditz glider extends beyond escape attempts. It represents the culmination of prisoner ingenuity at the camp known for escape creativity. Multiple tunnels, forged documents, impersonations, all techniques developed at Colditz influenced post-war security protocols. But the glider stood apart. It wasn't adapting existing techniques. It was creating entirely new capability, flying over walls that couldn't be tunneled under, bypassing guards that couldn't be fooled, exploiting three-dimensional space in a way German security hadn't considered. Modern military intelligence training includes the Colditz glider as a case study in thinking outside constraints. Security systems focus on expected threat vectors, tunnels, disguises, forged papers. The glider represented a completely unexpected approach. That lesson applies to modern security design. Don't just defend against known techniques. Consider what creative adversaries might invent. The Germans secured Colditz against every historical escape method. They never imagined prisoners would build an aircraft. The engineering principles demonstrated at Colditz remain relevant, working with constraints, improvising materials, designing without testing, managing projects covertly. These challenges appear in modern contexts beyond military applications. Disaster relief engineering faces similar constraints: limited materials, no testing facilities, urgent timelines. Engineers applying lessons from historical constraint-based projects like Colditz make better decisions. The Colditz glider also demonstrates the power of theoretical knowledge. Goldfinch never built a glider before. He worked from university textbooks memorized years earlier, but he understood the principles deeply enough to apply them in completely different context. That depth of understanding, theory translated to practice under pressure, represents education's ultimate value. Not just memorizing facts, but internalizing principles that can be applied creatively when circumstances demand. Today, aviation museums worldwide display replicas of the Colditz glider. Engineering schools use it as a teaching example. Security planners study it as a cautionary tale, and historians preserve it as evidence of human creativity under oppression. The glider that never flew achieved something perhaps more significant than escape. It proved that constraints, even extreme constraints like prison walls and guard towers, cannot limit human ingenuity. Given knowledge, determination, and creativity, people can achieve what seems impossible. The Germans built Colditz Castle as an unescapable prison. They gathered the most troublesome prisoners behind medieval walls. They established security procedures that had stopped every previous escape attempt. But they couldn't prevent prisoners from imagining flight, from calculating aerodynamics on scraps of paper, from stealing bedboards and sewing sleeping bags into wings, from building, in absolute secrecy, a working aircraft in an attic above a chapel. The Colditz glider stands as evidence that the human mind, when combined with engineering knowledge and persistence, can overcome any physical constraint. The prisoners didn't escape in the glider. The war ended first, but they proved they could have. And that proof, preserved in museum displays and engineering textbooks, teaches a lesson more valuable than any single escape. Sometimes the most important engineering projects are the ones that demonstrate what's possible, not the ones that achieve immediate practical success. The Colditz glider never carried anyone to freedom, but it showed that castle walls and guard towers are only barriers if you limit yourself to two-dimensional thinking. When you add the third dimension, when you think about flight instead of tunnels, when you apply engineering principles instead of accepting physical limitations, the impossible becomes merely difficult. And difficult, for engineers like Goldfinch and Best, just means it takes longer.